Here is part 2 of the stoichiometry notes. Starting with the empirical formula, figuring out the empirical formula of a organic compound, carbon, hydrogen, oxygen containing compound that was combusted. Basically, the way that it works and the reason that it works is because, you know, if you have a compound containing carbon, hydrogen, and oxygen, so let's say it has this formula right here, and you combust it, meaning you react it with oxygen, you're going to produce CO2 and H2O. And we know that all of the carbon from our unknown compound is going to go into the carbon dioxide. So we can use whatever amount of carbon dioxide that we got, convert it to moles, which means that's how many moles of carbon we had back here. And flip side of that, we know that all the hydrogen from right here went into the hydrogen in the water vapor. So however much water vapor we produced will tell us how many hydrogens we have. And then the other thing that we need to know is the starting mass of this compound, and then we can subtract out how much carbon and hydrogen and know that whatever's left over has to be oxygen. So it looks like this. We have this size sample. So we're going to need this information right here, of a compound containing CHNO, yields 7.832 grams of carbon dioxide and 1.922 grams of water upon combustion. What is the simplest formula of the compound? Well, the first thing that we're going to do is figure out how many moles of carbon are contained in this many grams of carbon dioxide. So 7.832 grams of CO2. If you don't have the molar mass of CO2 memorized yet, you will by the time this class is over. So the molar mass of carbon dioxide is 44.01 grams. And then from each mole of carbon dioxide, we're going to get 1 mole of carbon. And this works out to 0.178 moles of carbon. So that's how many moles of carbon we got going on right now. And then take the other number, the 1.922 grams of water, and convert that to moles of hydrogen. So each mole of water has a mass of 18.02 grams. And from each mole of water, we're going to get 2 moles of hydrogen. And that is going to work out to 0.217 moles. Actually, I can get 4 sig figs in there, can't I? So 2.13, well, I wrote that totally wrong. 0.2136 moles of hydrogen. So we know our formula so far is C.178 H 0.2136, and O is still unknown. So what we're going to do, we know that we had 3.489 grams of our original sample. Well, of that 3.489 grams, 0.178 moles of it is carbon and 0.213 moles of it is hydrogen. So I'm going to convert these guys to mass of these individual elements. So for carbon, each mole is 12.01 grams, and for hydrogen each mole is 1.01 grams. And so that works out to 0.178 times 12.01 is 2.14 grams. And then for the other one, 0.2136 times 1.01 is 0.215, we'll just say 0.216. And that's grams of carbon. This is grams of hydrogen. So we had a total of 3.489, but this much of it was carbon. Whoa, I don't know why I wrote a C there, sorry. And this much of it was hydrogen, so I'm going to take 3.489. I'm going to subtract that 2.14, and I'm also going to subtract the 0.216, and what's left behind is 1.13. So I know that I have 1.13 grams of oxygen, so I need to figure out how many moles that is. So every 16 grams of oxygen gives me 1 mole. And that is going to be equal to 0.0706 moles. So I now know that oxygen is 0.0706. But of course, I can't have a formula written like this. So to get it into the simplest whole number formula ratio, I'm going to take all 3 of these and divide them by the smallest one, which is the 0.076, and 0.178 divided by 0.0706 is going to give me C2.5. 0.2316 divided by 0.07 is going to give me H3, and then of course O becomes 1. Can't have a 2.5, so take this whole thing, multiply it by 2, and my final formula is C5H6O2. A hydrate is a type of compound, an ionic compound, where you have water attached to it. And the formula is written with the formula of the ionic compound and then this lovely little dot and then however many water molecules are attached to it. When you heat a hydrate, the extra water molecules are evaporated off and then you're left with the anhydrate. So you can use this information to calculate how many water molecules are in a hydrate by comparing the masses of the anhydrate after heating to the mass that you started with, the hydrate, before heating. And this will be another lab that we do eventually with actually this compound right here, copper 2 sulfate. So we started with 21.91 grams of copper sulfate hydrate. We don't know how many waters are attached. We heated it to the point that all the waters were driven off and we were left with the white CuSO4. This is a really, really pretty blue color. Get rid of the waters and you're left with this white powdery thing, plus an unknown number of water molecules that were evaporated off. So if we had 21.91 grams of this stuff, we have 14 grams of this stuff. Well, how much water do we logically have to have? According to the law of conservation of mass, we had to have 7.91 grams of the water. So if we want to figure out this X right here, we need to convert both of these guys into moles. So let's go ahead and do that. So taking the 14 grams of copper sulfate, copper 2 sulfate, convert that into moles using the molar mass, which is 159.5 grams per mole, which works out to 0.0878 moles of copper sulfate, 2 sulfate. And then for the 7.91, we do the same thing. Notice how every time that we're given a mass, we inevitably end up converting it to moles. Kind of do that on everything in chemistry. Molar mass, again, of water is 18.02 grams of water per mole. And this works out to about 0.439. Of course, can't have these numbers going on, so we divide both of them by the smallest one. This becomes 1. Divide this by 0.0878, and this works out to something real crazy like 5.00067. I don't know, something like that, but basically 5. And so our X up here is 5. It's copper 2 sulfate pentahydrate, and so we would have 5 water molecules released per mole of copper sulfate. So that's how that one would work. Okay, finally, we're at stoichiometry. In order to do a stoichiometry calculation, you have to have a balanced reaction. You've got to pay close attention to sig figs, and the biggest thing of all is you've got to keep it organized. If you don't like the box thing that I do, that's totally fine. There are hundreds of other teachers out there that do something besides the box thing. So you just pick the method that works for you and stick with it. So, it's a real simple example. How many moles of octane will burn in the presence of 37 moles of oxygen? To do the formula for octane, C8, and then to know how many H's it is, if the suffix is an A and E. You know, it's all single bonds. And so to figure out how many hydrogens, you take the number of carbons, multiply it by 2, and add 2. So 16 plus 2 gives us 18. Multiply by 2, add by 2 tells you how many hydrogens. We're going to react that with some oxygen to produce carbon dioxide and water. To balance this guy, whenever we're balancing these kind of combustions, I always start with carbon. So I have 8 carbons over here, stick an 8 right there. Then I go on to my hydrogens, save my oxygens for last since they're over here by themselves. I have 18 hydrogens, so I need to do 9 over here to give me 18. And then this gives me an odd number of oxygens, 25 to be exact. So to get O2 to be an odd number, I would have to multiply it by 12.5. Can't have a coefficient of 12.5, so I'm now going to take this entire equation and multiply it by 2. So that means the actual equation is 2C8H18 plus 25 oxygens gives us 16 CO2s and 18 waters. So the question is, if you have 37 moles of oxygen, how many moles of octane will burn? So for every 25 moles of oxygen, we're going to burn 2 moles of octane. And that works out to, let's see, 37 times 2 divided by 25 gives us 2.96 moles of octane. Okay, next thing that we have to do, next example, same equation, so go back and get the equation if you need to. We have 695 grams of octane, which is about equal to 1 gallon. And we're going to calculate how many grams of carbon dioxide are obtained. So we're going to see how much carbon dioxide is produced from burning 1 gallon of octane. The molar mass of octane is what we're going to start with because we need to convert this to moles. So the molar mass of this particular compound is something 114. Yeah, that's plenty. Grams of octane to every 1 mole. And if you remember from the equation, for every 2 moles of octane, we're going to get 16 moles of carbon dioxide. And for each mole of carbon dioxide, we're going to have a mass of 44.01 grams. So cross stuff out. Reduce if you can. The 16 and the 2 can reduce each other, so the 2 goes away and the 16 becomes an 8. And then you plug this in and you get incorrect sig figs. You're only allowed 3. 2,150 grams of CO2. I think it actually works out to like 2,140, high 40s, something like that. But we're only allowed 3 sig figs, so 2,150. And so 2,150 grams of CO2 is released for every gallon of octane. Gasoline. If you're going, what's octane? Last thing I want to talk about is limiting reactants. And actually, you know what? I think I'm going to go ahead and cut this one off and have a part 3.